It's a pleasure to have Jose Simental, who will conclude this series of lectures about, and his talk will be about cluster algebras for general braid varieties. So thanks to everyone who's still here. Go ahead.
Well, thank you. Thanks to everyone who's still here, indeed. And thanks a lot to the organizers for inviting me. I do feel a bit like a fish out of water because I am decidedly less symplectic than both Roger and Dapping. And so will my talk be less symplectic than their talks. Nevertheless, I hope I can still catch your attention. And I also hope that you're all over 18, because this talk will also be very explicit. So we will go to explicit computations and how do you actually go and compute these cluster variables that Roger was talking about in the previous talk. So let's get into it. I have one modest goal for this talk, which is to build on what Dapping mentioned in the double-bot Samuelson case and prove the more general case, which is that if we have a positive braid on n strands, then the coordinate ring of the braid variety, this x beta, is a cluster algebra. By this, well, there are a few things that we need to do if we want to say that something is a cluster algebra. Remember that a cluster algebra is equipped with many sets of generators that are in seeds. So if we want to say that something is a cluster algebra, we need to at least build one seed. And that is what we're going to do. We're going to build an initial seed for this algebra, which means that we need to build some algebraically independent regular functions, enough of them. And by enough, I mean as many as the dimension of this variety. And it is essential that these functions will be regular. So they need to be in this algebra. After that, we also need to produce a mutation rule. So once we have a cluster, we need to say how to produce more clusters from the initial one. And combinatorially, this will be given by an ice quiver, meaning a quiver where we declare some of the vertices first, meaning that we cannot mutate at a certain vertices. And finally, we need to verify that after we mutate once, then we still have regular functions on the braid variety. So this is the list that we need to do. There is a bit more work after that to say that really this is a cluster algebra, but this is like the list that we should do if we want to claim that something is a cluster. Okay. So let me start by recalling this variety and giving an affine presentation for it. So we start with a positive braid on n strands. And by the braid variety, I mean the modular space of L+1 tuples of flags in C to the n, subject to three conditions. I want to start with the standard flag. So when I say C to the n, I imagine that I already have a coordinate basis. And I want the first flag to be the standard one. I want the last flag to also be a coordinate flag, which is as transverse to the standard flag as the braid beta allows. I will be a bit more explicit on what do I mean by this. And finally, I want that if I have the flag fj-1 and the flag fj, then they differ on the ij subspace, where ij are the letters of the braid word. Okay. Let me say something about condition 2. If any two strands cross in the braid diagram for beta, then this condition 2 will simply say that the last flag is going to be the anti-standard. And in this case, in the case when any two strands cross in the braid diagram for beta, then this variety is precisely the modular space of rank 1 sheaves on R2 with microlocal supports on the -1 frame closure of the positive braid beta delta. Okay. The case that Dapping talked about is when we have something like the -1 frame closure of the positive braid delta beta delta. So this is the main difference that actually does create many problems, that with Dapping, we cared about braid varieties of braids of this form. And now we don't have this standard delta to play with. That's one of the main differences. Okay, now let me give a very explicit presentation of this variety as an affine variety. So for that, let us recall that if we have a flag that is presented by a matrix, by this I mean that the ith subspace is spanned by the first I columns of the matrix A. Then the set of all flags that differ from this flag on exactly the ith subspace is an affine line. And we can parameterize this affine line again by matrices of this form, A, Bi of C, where C is a complex number, and Bi already appeared in Roget's talk, is this matrix that looks like, well, technically I guess I should have put like identities here, except in the I and I plus first row and column. So this is rank 2 computation essentially, and it's not hard to see that we have this. But I do want to give a warning that this parameterization depends on the initial matrix A. If we have another matrix such that, let's say, the two flags are the same, it is not going to be true that these flags are the same, but we don't need to make a change of variables here. And this is important when we compute all the cluster variables. Nevertheless, let's actually start. Well, remember that we start with the standard flag, and there is a very natural matrix that represents a standard flag, which is identity matrix. So we start with the identity that represents the standard flag F0, and then F1 is going to be represented by identity times Bi1, C1 for some number C1. Second flag, well, we now need to change the I2 subspace and so on. So we get these matrices representing each one of these flags in the braid variety. And with these conditions 1 and 3 are going to be satisfied. We start with the standard flag, and two consecutive flags differ precisely as we want them to differ, as it is specified by the braid beta. We need the last condition, that is that the last flag is also a coordinate flag, which is determined by the braid betas, transverse from the standard flag as beta allows. And this says that this matrix, delta inverse times this braid matrix, the beta of all these coordinates, is upper triangular, where this delta is a permutation matrix representing this this coordinate flag that can be obtained by the braid beta. I will be a bit more precise on what I mean by this. But coming back to the case that is of interest for symplectic geometry, which is when any two strands cross in beta, then this matrix delta is simply the anti-diagonal permutation matrix, which says that the last flag is the anti-standard flag. And all of our cluster variables, all of our computations will be in terms of these coordinates, C1 up to CL. So the cluster variables will be given as polynomials in these C variables. Okay. And as I guess it is clear by now, an essential ingredient is going to be the weaves that Roger talked, but I will restrict to a family of weaves that have already appeared that I'll call Demasur weaves. To me, what distinguishes Demasur weaves is that I imagine them as being oriented down. So I always imagine these strands as being oriented down. In particular, I will sometimes say about incoming vertices to what, sorry, about incoming edges to a trivalent vertex. And by this, I mean that these two are the incoming and this one is the outgoing. In general, if you are given just some weave with boundary a circle, it cannot be oriented in this way. And those that can be oriented are the ones that we call a Demasur weave. And I should also point out that up to equivalence, there are only finitely many De Maistre weaves, because somehow we are simplifying the braid word beta from top to bottom, and there is only a finite number of ways to simplify it. When we allow more general weaves, then it is true that we can access infinitely many seeds. But for what I will speak about, we are still in finite world, still very, very flexible, and we can access many more seeds than from more traditional combinatorial methods, such as Plavik graphs, but still finitely many. And of course, we should imagine these two leftmost diagrams as encoding Reidemeister moves. And I will say a few more words about this last part of the weave in a few minutes, because this will be the key to build the cluster variables. Everything interesting about the weave, at least algebraically, happens at these parts of the weave. Okay. And we will also imagine weaves, such as this one, as encoding the solution to a model A problem. So now we have this rectangle, and we want to fill in each region of the rectangle with a flag in such a way that on the region to the left, on this region, we have the standard flag. On the region to the right, we have a coordinate flag, which is as transferred to the standard flag as beta allows. In this case, we just have the anti-standard flag. And if two regions are separated by a string of color I, then we want the flags to be different in precisely the ith subspace. And with this, it is very easy to see that if I just look at the top part of the weave, then I have an element, then I have an element in x of beta. And we can propagate this element in x of beta to fill every region of the flag. We won't always be able to do so. And that is because of these trivalent vertices that actually give us some conditions on what we can put on top. For example, it is easy to see that here we cannot have the flag F2 being equal to the flag F4. That's a restriction that this top trivalent vertex is giving to us, and so on. But everything else is fine. We can just propagate. Let me come back to the first slide to explain a bit how we propagate the flags on top to just fill in the entirety of this weave diagram. So let's say that we are in this diagram, and just let's say that I is 1 and j is 2. So we are in flags in three-dimensional space that I will projectivize. So a flag is just going to be a point inside a line in P2, in CP2. So I start with a point inside a line. And crossing this strand tells me that I need to change the point, but keep the line, right? So I keep the line, and I change the point. Then 2 says that I need to keep the point, but change the line. And then I need to keep the line and change the point again. And with this information on top, I claim that there is a unique way to fill in which flags should go in these two regions, which now is pretty easy because here I need to keep the dot. So I keep the dot. I also keep this dot. And now it's easy to check that these two dots are different and there is a unique line passing through both of them. So, and it is the line that I should have. Okay. So every time we know the weaves, the flags on top of this diagram, we also know the flags on the bottom. They're uniquely determined. Same for this. This is slightly easier because now we're changing the ith and the kth subspace, but I and k don't talk to each other. So there is, again, a unique way to fill in this region if we know what is here, here, and here. But the trivalent vertex is actually a condition. In the trivalent vertex, I have a flag, let's say F1. I change the ith subspace to get to F2, and I change the ith subspace again to get to F3. And this is giving me the that I cannot change back to what I had before. So F1 and F3 are actually different. And this is telling me that if I just start with any collection of flags on the top, in general, I won't be able to just fill in everything in such a way that is consistent. But those flags for which I can do it, they actually form an algebraic torus. And the dimension of the algebraic torus is precisely the number of these trivalent vertices in the weave, which is the dimension of x of beta. So we construct an open algebraic torus inside x of beta. And we would like for this to be cluster tori. In other words, we need to find a system of coordinates of this torus, which is given by regular functions on the entire braid variety. Okay. And for that, I need to, again, return to my coordinate CIs, to my coordinate system of CIs. And these weaves also encode some equations among these matrices that are an algebraic incarnation of these operations with flags that we can do. So, for example, this 6-valent vertex encodes the equation that if I have bi of C1, bi plus 1 of C2 times bi of C3, I can change I plus 1i to I plus 1i, I plus 1 at the cost of a small change of variables. So I exchange 1 and 3, and 2 gets changed in this way. Okay. Similarly, this second one is even easier because, again, I and k don't talk to each other. These two matrices are going to commute. And the trivalent vertex, I emphasize, it's actually a condition on these variables. We can only draw the trivalent vertex when this C2 is not equal to 0. And in this case, this vertex is giving us the equation that bi of C1 times bi of C2 is bi of C1 minus C2 inverse, so I need to invert C2, times some upper triangular matrix, which is not trivial. And because of this, things get a bit messy if we had, for example, more strings in the weave to the right. So let's say that we have here C3 and C4, we would need to move this upper triangular matrix U past a BK of C3. And then this coordinate C3 would also change here, and the same for C4. And things get a bit messy to the right of the trivalent vertex, but they're still very computable. You can still tell a computer to compute all of this. And I also remark that this condition that C2 is not 0 is necessary and sufficient to build this trivalent vertex. It's easy to check that bi of C times bi of 0 is upper triangular. So if you have, let's say, C here and 0 here, the flag here and the flag here would be the same, and then we cannot draw the trivalent vertex. We can maybe extend the concept of a weave and allow for this sort of cups, but that will give us different type of surface, and it won't give us a torus inside the braid variety. So I want to do that. And with this, well, one natural idea then, as we can see, these variables that are coming on the right of a trivalent vertex are actually very important, and they are what are giving us the conditions of being able to fill in the weave. So those receive a special name. They call it the S variable. Every time we see a trivalent vertex, we can just do all these equations with matrices. The right incoming arm of this vertex is going to have some rational function, and we call that rational function the S variable. And the first impulse is to say, well, this should be the cluster variables, and it's very easy to see that the impulse is wrong because we want the cluster variables to be regular, and these variables are in general not regular. Let me do this example, which is a very baby example in detail, because I think many of the main ideas are already present in this baby example, although the technicalities become much more complicated. So we have this width, and we have the S variables, which in this case are S1, C5, C4 minus C5 inverse. We see already S2 is not regular. Then S3 is C3 minus the inverse of C4 minus C5 inverse, and so on. So the S variables are not regular. But in this example, it is pretty easy to see that the following variables are regular. We have S1 times S2, S1, S2, S3, and S1, S2, S3, S4. They are all regular. And not only they are regular, but they are what I call a cluster configuration for this quiver. Meaning that every time we mutate according to this quiver, we are going to get still regular functions on the braid variety. Let's do a few examples. So if we do, for example, if we want to mutate at the vertex number 1, so we have the new variable. It's going to be something divided by A1, and that something is the product of the cluster variables on the outgoing arrows, which is 1 in this case, plus A2 over this. And here it's easy to see that we have C4, which is, of course, regular because it's a polynomial indices. Similarly, if we do A2 prime, this is going to be A1 plus A3 over A2. And in this example, we can check by hand that this is going to be C3. And if we mutate at vertex 3, A3 prime, this is going to be A2 plus A4 divided by A3, which is C4. So we can mutate at each one of these variables, and we still get something regular. And moreover, note that because of this, we have all these variables, C5, C4, C3, and C2, already being contained in the cluster algebra for this quiver. There is still one more variable, which is C1, but one can check that C1 is A3 times A4 inverse, and A4 is invertible. So in this case, we can show by hand that the cluster algebra is precisely the algebra of functions on the braid variety. We can get every function on the, well, we can get every CI as being inside the cluster algebra. And I also would like to remark that these functions A1 up to A5, they're precisely, sorry, A1 up to A4, they are precisely the microlocal merodromies that the Ping talked about for the following cycles. And A4 is special because it is frozen, but we still have this sort of cycle with boundary, A4. And we see that this quiver is precisely the intersection quiver of these cycles. Okay, so this was a very baby example, but we can recover at least one idea from here. We have the S variables, and the cluster variables should be monomials in the S variables. And the monomials should be in such a way that the change of coordinates is upper triangular, so that we can still have a basis of these cluster terms. The problem, of course, is how do we find these change of variables? Number one. And number two, how do we find a mutation? And we're going to solve these two problems at the same time for a specific class of widths that we call an inductive width. I will define them in a second. I just want to point out that the choice to have inductive weaves is only for the presentation. Things are much easier. We actually have a way to obtain cluster variables and cycles for any Demaster weaves. It's just that for a general Demaster weave, it's much more complicated to get the cluster variables. In this case of the inductive weaves, we can actually use the S variables that are very natural to construct the cluster variables. Okay. Before I go there, are there any questions or comments? Okay, so we're going to define two weaves for beta. The first one is the right to left inductive weave. In a nutshell, is what you get by reading the word beta from right to left and putting a trivalent vertex as soon as you can. More precisely, we define this inductively. The right to left inductive weave of the empty braid word is the empty weave. And if we have already defined the weave for beta, then we define the weave for sigma I beta as follows. There is some braid word at the bottom of the weave, which is delta, and it's precisely the same delta that appeared in the equation defining the braid variety. If this word sigma I delta is reduced, meaning that in the braid diagram for sigma I delta, no two strands cross twice, then the inductive weave for sigma I beta is just going to be the inductive weave for beta, and you append an I-core strand on the left. Completely disjoint. That's fine. But if it is not reduced, then we can find a braid word for delta that starts with sigma I. In this case, we have, I will do an example in a second, but we have W beta, then we can do this because we can find a braid word for delta that starts with, let's say, blue. So we can do this trivalent vertex. And then we keep building this weave inductively, reading the word right to left. Let's do an example. So let's say 1 is blue, 2 is red. We start with, remember, it's from right to left. So we start with sigma 1. So we just have that. Then we add the sigma 1. Well, we append this thing here. And for the next sigma 1 with this, then we do sigma 2. And this word, sigma 2, sigma 1 is reduced. So this is the inductive weave for this word, sigma 2, sigma 1, sigma 1, sigma 1. We keep going. Sigma 2. Again, this word is reduced, so I don't do anything. But in the next one, this word is not reduced. I can do a Rademacher move. And I can do this. Similarly, I can do this. And then I can do another Rademacher move to make this 2, 1, 2 a 1, 2, 1. And this is the right to left inductive weave for this word. In terms of flags, what this is trying to tell us is that each flag here, so here we have the anti-standard flag, each flag is as far from the anti-standard flag as it can theoretically be given the braid word. Okay. We want the first flag to differ at the first subspace from the anti-standard flag, but also, well, first reading from right to left, but also this flag and also this flag and so on. Okay. But of course, we can also read the braid word left to right, and we get another inductive weave. That is the left to right inductive weave. The definition is the same. We just read the word backwards. So in this case, we have sigma 1, sigma 2, sigma 2, sigma 1. So now we have this width. Okay? And the condition now is sort of dual to the right to left inductive width. Now here we have the standard flag. And the condition is that each flag is as far as it can theoretically be from the standard, given the braid world. Okay, these form two distinguished tori, and these are the tori that we're going to. Now, as Roger mentioned, we have this concept of Lusztig cycles that are cycles on the width defined by some very precise and very concrete rules. I don't need to have inductive widths to do this. This works for any dimensional width. So for each trivalent vertex, V, we are going to have a cycle, which is just going to be assigning a number to each edge of the width. If you want to pair it with the talks of Roger and the Pink, we have cycles on the widths, and this is going to tell us the multiplicity of the cycle on this width. So this is defined as follows. We have fixed this trivalent vertex, V. For any edge above V, we have the value of the cycle being 0. And for the outgoing edge of V, the value of the cycle is 1. So this is telling us how to start the cycle. So this is the trivalent vertex V. Here we have 0, 0, and here we have 1. And now below V, this cycle satisfies some tropical version of Lusztig's coordinates in Lie-theory, which in pictures are as follows. If we know what are the values of the cycle, let's say here and here, then in the outgoing edge is going to be the minimum of those. For example, in the left to right inductive width, such as this one, the value of A2 is always going to be 0. So here we just have A1, 0. And that's partly why these inductive widths simplify things. Similarly, if we have this move, well, the cycles shouldn't talk to each other. The values of the cycles should not talk to each other, and they don't talk to each other. They just pass by. And the most complicated one is what happens when we have this Rademacher tree move. And here we have the rules. Let me just be explicit in some cases that are the most important ones. So let's say that A is 1, B is 0, and C is 0. Then at the bottom, we have, well, B plus C is 0 minus the minimum, I get 0, 0, 1. Which is part of the picture that Roger drew. So I have a cycle incoming here. It just moves through. Okay. And it is similar if I start with a 0, 0, 1. It just moves through like this. And the other interesting behavior, sorry for this, is when I have 0, 1, 0. In this case, B plus C minus the minimum is 1, 0, 1. So in this case, I have a cycle coming here. And I say that the cycle bifurcates. So these are very precise rules on how to draw the cycles in the width. If we have something coming on the left edge of a 6-valent vertex, it moves through the right. On the right edge, it moves through the left. And in the middle, it bifurcates. And we can draw a cycle for every trivalent vertex. Let me do an example. Let's do, for example, the top trivalent vertex. I won't do all of them. So in the top, I start here with 0, 0, 1, right? And let me just color the edges where the value is not equal to 0. Then, as I mentioned, when I enter a 6-valent vertex through the middle, we bifurcate. Now we enter on the left a 6-variant vertex on the left. So we go through, we enter a 6-variant vertex on the left, sorry, on the left again. And here, because the value here is 0, the cycle stops. And now here again, we bifurcate, the cycle stops, and the cycle stops. And we can compute this for each trivariant vertex. Each trivariant vertex comes with its own cycle. These are pictured on the right with colors. In this particular case, each cycle takes values 0 or 1 in each edge. So I just color the edges where the value is 1. But this doesn't need to be the case for more general weaves. For more general weaves, we can see multiplicities of 2 or higher on the cycles. Okay. So we have managed to produce these cycles. And with these, according to Roget's creed, now we can compute the intersection of these cycles to at least get a quiver. Sorry, before that, there are a few special cycles here, which are the cycles that somehow fall all the way to the boundary of the weaves. In this case, we have this cycle, the black cycle goes all the way down, this aqua cycle, and the yellow cycle. And we call these cycles frozen, because they will be frozen variables in the cluster search. And each cycle which is not frozen is mutable. So the mutable cycles are absolute cycles, and the frozen cycles are relative to the boundary, essentially. Okay. And now we can define the intersections of these cycles. We can do it in 2 ways. We can actually go and draw the cycles in the weave, but we can also give very precise rules on how to compute the cycles. The intersections. 2 cycles will intersect at either a trivalent or a 6-valent vertex. Because again, the 4-valent vertices, they are far from each other in the actual weave. And we have determinantal formulas to compute this. I won't go over them, just believe me that they actually do compute geometric intersections between these cycles. Okay. It is usually enough to consider the following rules. If we have this aqua cycle coming on the left and this pink cycle coming, this intersection is going to draw an arrow from the aqua to the pink. And same so we have an arrow from here to here. Similarly, we have an arrow from here to here, or we have an arrow from here to here if the cycles come on opposite arms of a 6-valent vertex. Okay. These are completely the intersection rules that Roger was talking about, but now we can make them more algorithmic. And now we have a quiver, such as this one for this weave. Here we see, for example, there is one intersection between the pink and the blue at this vertex. There is one intersection between the blue and the green at this vertex, but there are 2 intersections between the green and the pink, which happen at these 2 6-valent vertices, and they both go in the same direction. So we obtain this quiver, and I want to emphasize that these 3 vertices, so that's why they have like a blue rim, these are frozen. So starting from a weave, and in this case, we have a left-to-right inductive, but this can be really any Demasur weave. We have managed to produce a quiver using these sort of cycles in the weave and intersections between. And it turns out that these cycles are also helpful when defining the cluster variables. So let's take a weave such that for each trivalent vertex V, so we have a trivalent vertex, either the left arm or the right arm go straight all the way to the upper boundary. So we have either this or we have either this. Example for this is the left-right inductive, and examples, sorry, the other one, the right to left inductive with. An example of this is the left to right inductive. Then for each trivalent vertex, we take its S variable and multiply by all the cluster variables that we assume are already defined of things coming towards this vertex. Okay. The claim is that this is a regular function on x of beta, and together with the intersection form, these things give a cluster structure on x of beta. And something that I found quite surprising is that if you remember these these S variables are defined as rational functions in the variables ci up to cl. And one can check that this cluster variable is in fact a polynomial in the ci's. So for example, let's say here I have some S variables, S1, S2, S3, S4, S5, and S6. And S1 is actually going to be regular because it's the first S variable, and this is going to be C5. This thing. Then S2 is going to be the S variable, sorry. Then A2 is going to be the S variable S2 times the cluster variable A1, because we have this pink in common here. And the third cluster variable is going to be S3 times the cluster variable A2, and so on. This is an upper triangular change of variables. And in fact, at least in this example, we can actually compute and see that we obtain these cluster variables that are polynomials in Cs, and therefore they are manifestly regular on the entire braid variety. And well, we should also verify that once we mutate once, we still get something regular. And if you ever get bored, you can actually do this. We notice that we get polynomials. And I want to emphasize something. Technically, the algebra functions on the braid variety, well, this is polynomials in this Cs modulo an ideal, where the ideal tells us that this matrix is upper triangular. If you want to compute this, you will not use the relations defining I. These are already valid in the polynomial algebra. Which is something I believe, I mean, I know Roger was saying that we obtain in general quasi-cluster structures. Here we obtain an actual honest cluster structure. We are actually specifying the cluster variables. And part of the reason why I believe this cluster structure is special is this. You have polynomials in Cs, and every time you mutate, you get polynomials in Cs. You don't need to use the relations of I. This is all valid inside the polynomial. And well, I have presented how to compute the cluster variables, how to compute the quiver, and I gave you this example where things work nicely. A question now is, well, why does this work? So to explain why this works, we need to refer to Dapping's talk. First of all, let me set up some notation. Delta that has appeared throughout the day is going to be a lift for the longest element of Sn. So it's a half twist, right, if you want. And the first thing to check is that when we have a braid of the form delta beta, then choosing the left to right inductive width, we obtain the same quiver and the same functions that the ping presented in his talk. If I remember correctly, well, I wasn't here, but I saw his slides, that ping mentioned that you can obtain the cluster variables as minors of some matrices. And we can check that we obtain precisely the same minors. So in this case, at least, we know that we obtain a cluster structure. And I want to point out that this phenomenon of things being polynomial, it is already present in the work of dapping with Lin Hui Shen. In that case, you define the cluster variables using minors, and you can check that no matter how much you mutate, things are going to be valid always in the polynomial algebra. You don't need to use any relations. An observation now is that by the way we define the cluster variables, we can erase letters from the right of the weave of the braid without affecting the definition of the previous cluster variables and without affecting the definition of the previous mutation rules. So if I, for example, decide that I don't want this word, this last red letter, I can just delete it. And nothing really will happen to the previous variables. So we would have to delete this. And we would have to freeze this green one because now it will come to the boundary. But the formulas I gave for the S variables and the formulas I gave for the cluster variables and the formulas for the Lusztig cycles are not going to change. So things just don't change. So we would like to be able to delete this delta and just stay with the word beta, which is what we want. We cannot do it on the nose because we can erase letters from the right, but delta is on the left. However, we use that, we can always write this word delta beta in the form beta tilde delta, where this beta tilde is obtained from beta just by replacing sigma I with sigma n minus. It's just a half twist, so you half twist everything. So these two varieties are isomorphic, and we can compare the inductive weaves for them. At the cluster level, all the quivers and the variables for these two weaves, they are related by a sequence of mutations. And we can say precisely where to mutate, although this is a bit technical. So we start with the work of Dapping and Lin Hui to have this cluster structure for delta beta. We mutate a lot, and we know that by mutating, we don't change. We stay in the polynomial world. We mutate precisely so that now we are for the weave and variables of this, and then we can erase delta on the right. And this is going to give us some polynomials in Cs and a mutation rule for those polynomials in Cs, such that every time you mutate, you stay polynomial in the Cs. So at least by the starfish lemma that I believe Dapping discussed, at least we know that the upper cluster algebra is going to be contained in the coordinate algebra of the braid variety. We still need to verify that the coordinate algebra of the braid variety coincides with the cluster algebra. And this is the only place where we use the relations defining the braid variety. So we actually show that each CI is a cluster monomial. It's easy to see that some TIs have to be cluster monomials. For example, here, well, obviously, C5 is a cluster monomial because it's an S variable. It's an initial S variable. And we can keep rotating this braid so that not only C5, but C4, C3, C2, C1 is also a cluster variable in maybe a different cluster for a quasi-equivalent cluster structure. These rotations are only quasi-equivalences. However, quasi-equivalences, while they don't preserve cluster variables, they preserve cluster monomials, meaning those functions that can be written as a monomial of elements in a single cluster. So each one of the C's is a cluster monomial, therefore it belongs to the cluster algebra, and that's how we obtain that this C of x beta tilde, or although it doesn't really matter, is actually equal to the cluster. So the process is not really inductive, even though we call these weaves inductive weaves. The process is really use the fact that we know the result for braids that contain this delta, thanks to work of Dapping and Lin Hui, and then find a way to chop the delta. Okay. A few properties of this cluster structure. We cannot get any quiver by doing this, because note that the quiver for beta sigma I either coincides with that of beta if by adding sigma I we don't create two strings crossing more than once, or it is obtained by this one by the process of, well, we are going to add a new trivalent vertex. We have this weave W, then we add this new trivalent vertex. So we're going to add definitely one more frozen variable, which is the frozen variable that starts at this trivalent and goes down. But also there may have been some other variables that were not frozen, sorry, that were frozen, and now we have to thaw them. Those that now come here, oops, sorry, this is too large. Those that now may end here. Okay, so we always obtain the quivers by doing these things. We toss some vertices, some frozen vertices, and maybe add arrows between them, and add a frozen C. This is closely related to a class of quivers called quivers in class P. So we definitely always obtain quivers in class P. We cannot obtain anything. Number two, as Roger mentioned, this cluster structure admits a reading sequence and a DT transformation. The cluster structure always induces a cluster Poisson structure. In cluster Poisson structures, the cluster variables are not regular, they can be rational, and they're actually monomials in the A cluster variables. So it's fine. The exchange matrix has full rank. This cluster structure is locally acyclic, meaning that we can cover the braid variety with maybe not open sets of the form by spec A for A cluster algebra of an acyclic field. As I mentioned before, we can produce cluster coordinates associated to any Demasur weaves. The construction is significantly more complicated, but they all give seats in the same cluster structure. So we obtain many, many different seats in the same cluster structure. A few months after our work appeared, independent work of Pavel Galashin, Thomas Lammers, Sherman Bennett, and David Speyer also constructs a cluster structure on this variety. There are a few differences. I would say the main difference is that weaves are much more flexible than the combinatorics they use, and they allow us to access many more seats, even if we stay within the world of Demasur weaves. The combinatorics they use are a generalization of Postnikov's Plavik graphs. So Plavik graphs are bicolored graphs drawn in a disk. What they do is they do bicolored graphs now drawn in a surface of maybe topologically non-trivial. It would be very interesting to compare the two constructions. I do believe that we obtain quasi-cluster equivalent structures, but this needs to be verified. And finally, even though this entire day was really about type A, similar constructions can be done for arbitrary Lie type. The notion of weave still makes sense, even though we don't know whether there is a symplectic interpretation. We just have the 6-valent vertices and 4-valent vertices that the Dinkin diagram of the corresponding Lie type tells us. And we can also do this for non-simple lace types. Now, in non-simple lace type, we need to have not only 4 and 6-valent, but also 8-valent and 12-valent vertices, depending on what of what Lie algebra we are in. So I believe that we should be able to access a lot of these class P of quivers using these braid varieties for all Lie types. I don't know if we obtain any quiver in class P. I would be surprised, but at least a lot of them I am sure we can. And well, with that, thank you so much. And thanks for staying until the very end.
Thank you. Let's thank Jose for his talk. Are there any questions, or rather, while people are thinking about questions, let me ask some questions. The first thing I was going to ask, I'm sorry, this is maybe a side thing. You mentioned that at the beginning that if you allow some things that look like cups, you get some charts that are more general, that are not just C star to the N.
Yeah, we get some charts. Some charts that look like C to the number of these cups times C star to the number of.
Oh, that's great.
Yeah.
That's great. There's, I mean, in the A side, there's probably a symplectic interpretation of these things.
Yeah, I think, I mean, you also get, maybe Roger should verify this, but I think you also get some Lagrangians or said that they are not embedded.
Yes, that sounds great. Okay, they're immersed. Yeah. The other thing I was going to ask is, I just wanted to make sure, but this thing that you get multiple seeds for the same cluster thing, for the place cluster, whatever structure. Do you get all the seeds for this cluster structure from this construction, or?
That's a great question, as not with Demaster weaves in general, because Demaster weaves are finite in number.
Okay, yeah, of course.
I believe in finite cluster type, which you get for something like 2n torus links, we do get everything. Also, we should get everything, although I am not sure. Yeah, for links of type Dn, that I don't know if I can describe at the moment, and I don't know for E6, E7, and E8.
I see.
But one thing I can tell you is that even if we don't get everything, the toric charts for Demaster weaves are already enough to cover all the other toric charts for any weave. Yeah.
You get the entire variety.
Well, the toric part, it's important, I think, that there's a difference between the union of the cluster tori and the variety. Yeah.
I understand. Okay, any other questions?
So I have a question. I was confused by this Lusztig mutation showing up. So why does it show up?
That's an amazing question. I don't know. The way these rules appeared to us was by doing many examples and seeing that this is what appears. But I don't have any conceptual explanation as to why they should show up.
So if I understand right, you said you put something on the boundary and then you walk through this graph from up to down, and the functions which satisfies this Lusztig mutation, they are the vertices of the cluster quiver, right? Something
Yes.
like this.
Yes.
Okay, so because this Lusztig mutation can be translated to cluster mutation. So in some sense, the vertices resemble already some special tropical points in some kind of different cluster algebra. That's somehow weird.
Yeah, yeah, that's true. Yeah.
Okay, thanks.
Okay. Any more questions? Okay, well, then we should probably end the proceedings of the day and thank Jose one more time. Thank you.
Thank you.